so let's stick with that. So instead of the allele for altruism from before, we have an allele for green beard altruism. Now, when a blob with a green beard notices a predator, it'll only warn the other blob if that blob also has a green beard. So let's see whether this green beard strategy works in a simulation. And let's go back to the 50% chance of getting eaten after giving a warning. What do you think? Okay, that actually works pretty well. The green beard allele drove the cowardly allele to extinction, and decisively so. But again, we should test it with many runs and with different settings. I ended up testing the 50% and a 90% chance of getting eaten for 30 runs each. In each case, what do you think will happen? Alright, at the 50% death chance, it seems like our first run wasn't a fluke. The green beard allele does indeed have a massive advantage. One of the runs got a pretty rough start, but it still ended up taking over before too long. At 90%, things are pretty noisy. Only 10% of the acts of altruism actually end up saving an extra blob. So the random fluctuations are pretty dominant. And even though the average shows an upward trend, the green beard allele does go extinct in several runs. After seeing these, I was curious to try again, but starting with only a 10% frequency for the green beard allele. Once again, what do you predict? Will the graphs look the same, just shifted down to start at 10%, or will something else look different? In the 50% case, there are a few interesting things going on. After a while, we see that the average goes completely flat, because in every simulation, one allele or the other has gone extinct. Of the 30 runs, 11 had the green beard allele take over completely, and the other 19 had it go extinct. Even though the green beard allele had an advantage and saw its frequency rise on average, it's still subject to the whims of luck when there are only a few copies, and once extinction happens, it's permanent. It's interesting to imagine what kinds of alleles might have appeared in the history of the Earth and could have done well, but just got unlucky. The second interesting thing is that it seems like the green beard allele's advantage depends on how many green beards there are. Each run starts out with mostly random wobbling, but when the density of green beards gets higher, the helping happens more often and they get more benefit. And in the 90% chance case, things are just really chaotic, but we still do see an upward trend on average. Alright, so we have a simple version of green beard altruism working, but we should check to see how it does when things are just a bit more complex. Remember when I said earlier that in real life, behaviors are controlled by a complex interaction of many genes and environment over time? Well, we're not going to be able to capture all of that complexity here, but we can at least notice that this one green beard allele is doing kind of a lot. It doesn't just code for the altruism toward green beards, which is complicated on its own, it also codes for the green beard itself. So, as a small step toward a more realistic scenario, let's split those parts into two independent genes, each with two alleles. The first gene's alleles code for a green beard or no green beard, and the other gene's alleles code for altruism toward green beards or no altruism. And this means there will be four types of creatures. The blobs with no beard and no altruism will again be yellow and be called cowards. The blobs with no beard but altruism toward green beards will be blue, and they'll be called suckers. The blobs with a green beard but no will be blue, and they'll be called blobs with no beard but altruism toward green beards will be blue, and they'll be called suckers. The blobs with a green beard but no altruism toward green beards will be red and called imposters. And finally, the blobs with green beards who are also altruistic toward green beards will be green and be called true beards. And it's worth clarifying that even though these blobs are now different colors for tracking purposes, the blobs themselves can't see the colors, they just see the beards. Alright, to set up the next sim, we'll start with equal numbers of all these types, and we'll go back to the 50% death chance. Also, this time, let's just skip ahead and run it 30 times and look at the averages. But before we do, try making one last prediction. Okay, in this case, showing all the lines from every run just gives us this Jackson Pollock painting, so let's get rid of those lines and just look at the averages. So what happened? Well, the altruism allele gets eliminated pretty quickly, whether it's paired with a green beard or not. The first to go are the suckers. They help, but they never get help. It's a tough world out there. The true beards do alright at the very beginning, just like before, but they end up going extinct in the end, because they end up sacrificing themselves for the imposters. And the more imposters there are, the more a true beard is in danger of sacrificing itself. And then there are the cowards that just kind of mind their own business. They don't do great, but once the altruism allele is gone, there's really no difference between the imposter and the coward. So their relative frequencies just bounce around randomly for the rest of the run. So it seems like green beard altruism allele is gone, there's really no difference between the imposter and the coward. So their relative frequencies just bounce around randomly for the rest of the run. So it seems like green beard altruism breaks down with even a tiny bit of complexity. And as we'd expect from this, we've only found a few examples in nature. They aren't literal green beards, of course, but I've added some links to some papers in the description in case you want to learn more about them. Alright, those are all the systems we're going to look at in this video. To be honest, I actually find what we've seen so far to be a bit discouraging for making sense of altruism, especially in humans. We only found one type that worked at all, and it turned out to be really fragile in theory and rare in reality. But don't despair, we have a few more models to explore that are a bit more encouraging. And in the next video, we'll talk about kin selection, which follows Hamilton's rule. And while you wait for that video, why not level up your critical thinking skills with Brilliant? Brilliant has over 60 courses in math, science, and engineering, all with interactive components to help you learn deeply. And their courses are now available offline using their Android and iOS apps, so you can learn anywhere, anytime. I use Brilliant myself, and it's seriously really good. The first 200 people to sign up at brilliant.org/primer will get 20% off the annual premium subscription, and in the process, help support Primer. As always, thanks for watching.
W component. I've always found this a little mysterious, it's just what I've learned you have to do, so I'm going to come back to that in a moment. If we play the game now though, it at last appears as if you're actually looking out through the other side of the portal. They don't exactly take you anywhere when you walk through them though, so that's going to be the next task, right after I get some idea of what this W is doing in my equation. So I've been reading up on how 3D objects get squished onto a 2D monitor. To try and understand this a bit, I have a camera and a model plane. As long as the model is inside of these white lines, which is the camera's view frustum, the camera will be able to see it. Now, the camera has a projection matrix, and the goal of this is to squish everything in its view into a little unit box. If I apply that projection matrix, this happens. Not quite achieving the goal, but the result of the projection is actually a four-dimensional vector with the fourth component, or W component, being proportional to the distance from the camera. If we divide the position of each vertex by W, it's now inside the box. This box is useful because it's easy mathematically to tell if a triangle is outside the box, in which case the GPU doesn't have to waste time shading it in. And also, if we just ignore the Z component, we now have a completely flattened representation of our 3D model, which can be drawn to the screen. Hopefully everything I just said is accurate, because my understanding is still a little vague, but I think I've got a better idea now of what this perspective division is all about. I'd really like to learn more about the rendering process though at some point, because it's something I always just take for granted. All this talk of rendering does make me sympathize with the poor GPU that has to render not just the player's view, but also the view from every portal. One small thing I can do to alleviate its suffering is check if the screen of the link portal is visible from the player camera, and if not, I can skip rendering that thing. The visible from camera function will work by calculating the 6 planes that make up the camera's view frustum using the hand. find a geometry utility, and then check if the bounds of the renderer is inside or intersecting with those planes. I came across this technique on the Unity wiki, and while I have no reason to believe that Michael is trying to hoodwink me, it doesn't hurt to make sure that it's working how I expect. So I'll quickly make a 1x1 texture, color it red, and apply that to the screen if it's not visible. If it is visible, I'll set it back to the view texture. So now, as I look about, the portals should turn red the moment they're no longer in view of them.
Не совсем правильно. Что самое главное в росте? В росте. Наоборот, нет, наоборот. Что старый уже это все занять. Нет, наоборот. Вот это имеется в виду. Ну еще теперь. Наоборот, это свежесть будет, наоборот. И что это будет? Да нет, понял. Наоборот, люди. Нет, наоборот. Да. А, вот это он тебе. Ну вот это есть. Ну это есть проблема. Ну это нравится. Интересно. Тебя не понимаю. Это через коридор. Наоборот. Наоборот. Наоборот, нет. Нет, наоборот. Ну,